to our conference attendees. Good morning, everyone in the United States. Good day to everyone in Europe, and good evening to our conference attendees in Asia. We're going to start the last day of the conference with 3 exciting keynote talks. We don't have a plenary lecture today because we will have a very interesting panel discussion at the end of this conference day. You will see a few things that I bet you have never seen before, have not probably even known about MXenes. So stay with us till the end of the conference here. Today's topic is applications of MXenes. I am Yuri Gagotsi. I'm co-chair in this conference with Professor Michel Barzoum. For those of you who have not have not seen me before, speaking at other conferences here. And I will be the session chair and panel moderator today. Before we move to our first talk today, let me remind you about the webinar logistics. You have seen this slide multiple times if you have been with us for the first 4 days of the conference. Just a reminder that you can also connect by the phone. You are in a listen-only mode. You won't be able to ask questions or interfere in any other ways. But please ask questions by sending them to the chat box. I will select the most common, most interesting questions and deliver them to presenters here. And also, we will make recordings of the talks available after the conference here. With this, let's move to our first speaker today, and good friend and collaborator, Professor Gokshi Wang from the University of Technology, Sydney, Australia. He is the director of the Center for Clean Energy and a distinguished professor, very well known in the field of materials for energy storage and conversion. Gokshi, the virtual floor and pretty much the entire world online is yours now. We look forward to your presentation. Welcome.
Thank you, Yuri, for your very kind Thank you, Yuri, for your very kind introduction. Good morning and also good evening, ladies and gentlemen. Let's share my screen. And I bring presentation mode. And also I bring my laser point. Okay. Yuri, can you see my slide? I think it's okay. So today I would like to talk about the applications of MXenes for energy storage, okay, and conversion. So my name is Guoxi Wang. I'm from the University of Technology, Sydney. So firstly, I would like to congratulate Professor Michel Barzoum and Professor Yuri Gagotsi for establishing MXene 2D Wonder World. Firstly, I would like to briefly introduce my University of Technology Sydney is located in Greater Sydney. So after this pandemic, I would like to welcome all of you to visit Sydney and visit UTS. So I would like to thank my collaborators, Professor Yuri Gagotsi in Drexel University, and also Professor Yadong Li and Professor Chen Chen from Tsinghua University, China, and Professor Ruxi Liu from National Taiwan University in Taiwan. And I also would like to acknowledge my former PhD students, postdoctoral fellows for their contribution to this presentation. So today I would like to talk 5 different kind of applications, including MXenes for catalysis, MXenes for sodium-ion batteries, MXenes for lithium sodium sulfur batteries, MXenes for conversion chemistry-based batteries. Finally, I would like to introduce MXenes for desalination. Firstly, I would like to introduce our work, MXenes for catalysis. In 2018, we accidentally discovered we can deposit single platinum atoms on the surface of MXenes and form a very efficient catalyst for hydrogen evolution reaction. So why we needed to develop a single atom catalyst? Because the single atom catalyst have many advantages, including cost efficient, using minimum amount of precious metals. And, but the development of single atom catalyst faces many challenges, including preparation, very difficult to prepare single atoms, and also difficulty to maintain the stability. So in our work, we successfully using the electrochemical exfoliation method. Here we use a double transition metal MXene molybdenum 2 titanium carbon 2 mix to generate molybdenum vacancies for immobilizing platinum single atoms. And when we deposit the platinum single atoms on the MXene surface, the strong covalent interactions between the positively charged platinum single atoms and the MXene matrix lead to exceptional hydrogen evolution reaction performance and stability. So this is the electrochemical cells. We just put each max phase as one electrode and put platinum as the counter electrode. When you do the electrochemical, apply the voltage, sweep, and the MXene, each the max phase delaminated and become the MXene nanosheets. Simultaneously, platinum atoms dissolved in the electrolyte and migrate to the surface of the MXene phase and also finally deposit on the surface of the MXene phase. This is the SEM image observation. We observed this is a pristine max phase. You can see it's not detached, it's still compact. And when you do the electrochemical exfoliation, gradually you can generate cracks and the max phase materials gradually delaminate, and finally you can obtain well exfoliated MXene nanosheets. So then we further use HRTM and Hardif stem to analyze, to characterize the obtained MXene nanosheets. You can obtain 1 layer, 2 layer, or multi-layer MXene nanosheets. And also when you observe by Hardif stem, you can identify PT, platinum single atoms have been successfully immobilized on the surface of the MXene. And furthermore, we use synchrotron EXFS and XANES. We confirmed the platinum single atoms are positively charged. That means we successfully prepared the PT single atoms on the surface of MXenes. This is the the mechanism of the electrochemical exfoliation process. Basically, during the electrochemical exfoliation process, hydrogen gradually generated and then delaminate max phase and exfoliate max phase to individual MXene nanosheets. So this is the HER performance. From here, you can see the platinum MXene material catalyst demonstrate even slightly higher HER performance than commercial, the best HER catalyst, commercial platinum carbon catalyst. And when you analyze the mass catalytic performance, you can see the single atom, platinum single atom MXene catalyst demonstrate almost 40 times higher mass HER performance than commercial PT carbon catalyst. And then we did a calculation, DFT calculations. We found the hydrogen absorption energy on the surface of PT single atom on the surface of MXene is lower than commercial platinum carbon catalyst. That explained why the single atom PT on the surface of MXene can exhibit better HER performance. And then my friend in Tsinghua University, Professor Chen Chen, they did a similar work. In this case, we use a chemical method deposit PT single atoms on the surface of MXene nanosheets. We use this catalyst for functionalization of carbon dioxide. So this is the HRTM and Hadif stem analysis. You can see use chemical method. You can also obtain platinum single atoms deposited on the surface of the MXene nanosheets. And similarly, we use the synchrotron confirmed the PT single atoms are positively charged. That means we successfully obtained the platinum single atoms. And this, we apply this single atom PT on the surface of MXene as the catalyst for functionalization of carbon dioxide. We put aniline and carbon dioxide and triacyl hydrosilane, and then we successfully obtained a chemical called formaldehyde. So this is a very complicated catalytic chemical reaction, and also we did DFT calculations that explain the mechanism we proposed. So this is a MXene. You can see the MXene can have a very important applications for electrochemical catalysis. And then next, I would like to talk about MXenes for sodium batteries. So why we need to develop sodium-ion batteries? So sodium has unlimited natural resources, cheap and low cost. So if this battery system can be fully developed, it's ideal for large-scale energy storage and conversion. So this work was done by Xiuqian Xie. He spent 1 year visiting study in Yuri's group. He very smartly prepared MXene carbon nanotube composite paper with high volumetric capacity and sodium-based energy storage. This is the preparation process. Basically, the MXene nanosheets are negatively charged, and then we use CTAB surfactant to positively make carbon nanotube positively charged, and then we can self-assemble MXene nanosheets and carbon nanotubes. So this is a cross-section SEM view. You can see we obtained the sandwich structure. The MXene nanosheets sandwiched by carbon nanotubes prevent restacking of individual MXene nanosheets. And when we apply these materials as the anode materials in sodium-ion batteries, we achieved quite high specific capacity around 350 milliampere-hour per gram, and we are achieved more than 500 stable cyclability. And then later, Xiuqiang Xie collaborated with Meng Qian Zhao in Drexel University. They developed a method to use a hard template because the MXene nanosheet, individual MXene nanosheets are quite flexible. We can make hollow MXene spheres. So this is the SEM cross-section image. You can see when you make thin film, paper-like thin film, the cross-section composed of individual MXene, hollow MXene spheres. And this paper is flexible. And when we directly use hollow sphere MXene spheres as electrodes for sodium-ion batteries, you can see we can further extend the cycling stability to more than 1,000 cycles. And this is our recent work. We try to boost in sodium storage capability of MXene nanosheets. We add in phosphorine. Phosphorine is another kind of 2D materials, but because the phosphorus has a very high theoretical sodium ion storage capacity. So this SEM confirmed we homogeneously distribute phosphorine nanosheets small on the surface of MXene nanosheets. MXene nanosheets are large, size are large. And then we did a characterization, XRD and XPS. And then we test the electrochemical performance. You can see we can boost the sodium storage capacity to almost 600 milliampere-hour per gram. And particularly, we can achieve very high rate capability. In this case, at 1 amp per gram current density, we can discharge sodium ion cells for more than 1,000 cycles. And after cycling, we observed the thickness change of the electrode. When you directly use black phosphorine as the electrode, you can find after cycling, the electrode thickness increased dramatically. Surprisingly, when you use the composite, phosphorine MXene composite, you can minimize the electrode expansion from, in this case, just expand 4 micrometer. And also we did a theoretical calculation. We found that the MXenes have a very strong absorption energy towards sodium ions. And particularly we did in-depth XPS profiling, and we identified the fluorine participate the SEI layer formation. The fluorine is bring in by the MXene because when you each MX phase, you naturally bring fluorine and functionize the surface of the MXene with the fluorine termination functional group. So the fluorine is bring the benefit for stabilize the electrode and then extend the battery cycle life. And recently, we also did another work. We use MXene as a matrix to host potassium metal and then construct the potassium metal batteries. So this is the preparation process. We used a kind of defect containing and nitrogen doped MXene as a matrix combined with carbon nanotubes. And you can see the defect. This is the Hardif stem can clearly identify the defects. And also we did a calculation. We found the MXenes doesn't matter what kind of termination, functional group termination, hydroxide, oxygen, or fluorine, all these three kind of functional group terminated MXene all show quite strong absorption energy to potassium ions. And this is the electrochemical performance. You can see the MXene matrix can extend the cycle life of potassium electrode, and for other matrix like copper and aluminum or carbon nanotube gradually failed. And also we did the in situ XRD characterization and also the optical observation. You can see when you use copper, you substantially grew potassium dendrite, but when you use MXene as the substrate, no dendrite grows. So then we use MXene potassium metal electrode. We construct the potassium sulfur batteries, and also we achieved very nice electrochemical performance. Next, I would like to talk about MXenes for lithium sulfur batteries. So this work was done by Weichai Bao when he was PhD student at UTS, and also he spent 1 year in Yuri's group. And in this case, we did MXenes, doped MXenes by using melamine as a nitrogen source. We obtained a cramped nitrogen doped MXene, and then we load sulfur into these cramped MXenes and form MXene sulfur cathode. And this is the electrochemical performance. You can see when we use porous nitrogen doped MXene sulfur cathode, we achieve better electrochemical performance than stacked MXene cathode. And also we did a high sulfur loading. In this case, it's a 5.1 milligram per square centimeter sulfur loading, which is very high, considered in the field of lithium sulfur batteries. And also we achieved a very good cycling performance. And also we further did the absorption observation. You can see the nitrogen doped MXene can show strong absorption towards lithium polysulfide. That explains why the nitrogen doped MXene cathode can achieve better electrochemical performance. And this is another work done by Weichai Bao and collaborates with Dr. Chuck in Yuri's group. In this case, we prepared the sulfur-doped max phase in the first instance, and then we exfoliate sulfur-doped max phase to sulfur-doped MXene. And then we utilize this sulfur-doped MXene as the cathode host materials for sodium sulfur batteries. So this is a XPS characterization can clearly show sulfur has been successfully doped inside the MXene phase. And this is the electrochemical performance. You can see the sulfur doped cathode, MXene cathode show better electrochemical performance than the non-sulfur doped MXene cathodes. And also we did the DFT calculations. We found that the sulfur doped MXene show stronger, much stronger absorption energy towards different kind of sodium polysulfide. And then next, I will talk about MXenes for conversion chemistry-based batteries. So MXene can also be used for different kind of conversion-based chemistry batteries. In this case, we construct kind of quasi-solid-state MXene-based lithium iodine batteries. So the materials, cathode materials we prepared, we wrap MXene because MXene is flexible. The individual MXene nanosheet is extremely flexible. We can easily wrap individual MXene nanosheets on individual carbon fiber in carbon cloth. And then we can soak this MXene wrapped carbon cloth as a cathode soaked with iodine, and then use them as a cathode for lithium iodine batteries. And this is the theoretical calculation. You can see the MXene shows stronger absorption towards lithium iodine. And this is the electrochemical performance. You can see when we use MXene wrapped carbon cloth as the cathode, we can achieve very extremely good electrochemical performance up to 1,000 cycles. But if you don't use MXene wrapping, just using the bare carbon cloth, the electrochemical performance is very poor. The battery cells quickly failed on cycling. And recently, we also extended another application of MXene. In this case, we coated MXene nanosheets on the commercial separator for lithium selenide batteries. So here you can contact the angle. When you coat MXene on the PP separator, you can see the contact angle becomes smaller. That means it can improve the soaking property of the electrolyte on the separator. So also we did a DFT calculation, and particularly we did an in situ permission test. You can see when we use MXene coated separator, we found it can effectively prevent the permission of lithium selenide. And then we tested this MXene coated separator. We found this MXene modified separator can achieve much better electrochemical performance than when use the unmodified separator. So my last topic is related to MXene for desalination. So since the discovery of MXene, so MXene has been extensively used as the supercapacitors, because the MXene show very high, extremely high volumetric supercapacitance. So we think since MXene has a very high supercapacitance, if we use MXene materials as the electrode materials for capacitive desalination, it theoretically can achieve very nice performance. So we construct this kind of electrochemical cell for testing the capacitive desalination of MXene electrode materials. So here we use freeze-dry method. We can obtain porous MXene materials. So freeze-dry can efficiently, this method can efficiently prevent the restacking or elevate the restacking of individual MXene nanosheets. So this is the capacitance. You can see the porous MXene show very high supercapacitance. And then we applied the porous MXene and also restacked MXene and activated the carbon for capacitive desalination. You can see the MXene, porous MXene can achieve almost 10 times higher sodium chloride adsorption capacity than the commercial activated carbon. So therefore, I think the MXene is a very promising electrode materials for capacitive desalination. So finally, I will give my summary and perspective. So MXene is a class of versatile energy materials for catalysis and rechargeable batteries. MXene has a very high electronic conductivity, rich surface chemistry, tunable defects, and we can manipulate defects for catalysis application and unique physical properties. So if you consider chemical compositions, it's truly the MXenes can have several hundred varieties, even 1,000 varieties. You just do very simple mathematics. So in my opinion, the MXene's future is exceptionally bright. So finally, I would like to thank the funding agency in Australia for their financial support to my research on the MXene and the MXene applications, including Australian Research Council, ARC, Automotive Cooperative Research Center, AutoCRC, Australia Renewable Energy Agency, and the Real Manufacturing CRC. Thank you for your attention. I would be happy to answer questions.
Thank you very much, Professor Wang. Thank you for your excellent presentation. We have a number of questions received, and let me start with questions representing different topics that you covered in the presentation. The first one is related to the catalysis here. How can one induce single platinum atoms to MXene surface, and why don't platinum atoms merge into clusters or nanoparticles?
These MXenes is a double metal MXenes, is a molybdenum titanium carbide. During the electrochemical exfoliation process, we generate the molybdenum vacancies. And when you have the molybdenum vacancies, the platinum atoms immobilized exactly on that vacancies generate the single atoms. But if you extend the exfoliation time, we did obtain the platinum clusters. You have to nicely control the electrochemical exfoliation time.
Well, the next question related to the catalysis is about the environment for CO2 plus aniline reaction catalyzed by MXene. Was it gas, liquid, aqueous solution?
It's a gas liquid.
Gas meeting here. And what is the turnover number for MXene as catalyst in this reaction?
We didn't exactly do the testing of the turnover. We just quantitatively test this catalytic reaction.
Okay, let me switch the gear and move to sodium-ion batteries. The question is whether there is any side effect in terms of capacitance from employed CTAB, which was used as surfactant for the assembly.
I don't think there is some side effect. The surfactants could cause the irreversible capacity in the first cycle. Yeah.
Mm-hmm. Thank you. Another question, a couple of questions too related to the sulfur batteries here. In the sulfur-doped MXene work in sodium-sulfur batteries, you use the PCEC with FEC electrolyte. And it's known that carbonate electrolytes lead often to poor cycling because of dissolution of polysulfides and transfer of soluble polysulfides. Why does this process not happen in the case of MXene cathodes?
We did compare in my presentation. If we don't have sulfur doping, there is a problem. The cycling performance is poor. But when we have sulfur doping into the MXene phase, in this case, we start doping from max phase. So the sulfur doping not on the surface, on the lattice level. So we did a DFG calculation. When you have sulfur-doping, the MXenes show very strong binding energy towards sodium polysulfide. So that's can explain why the sulfur-doping is critical to achieve better performance.
And another question related to the metal sulfur batteries here is about the role of melamine in MXene in lithium sulfur storage.
Melamine, that is for lithium sulfur battery. The melamine, we use melamine as a nitrogen source to achieve a nitrogen doped MXenes. So after sintering, melamine decomposed and contribute nitrogen towards the nitrogen doping for MXene, achieve nitrogen doped MXenes. Yeah.
Mm-hmm. Thank you. And also a question related to your work on desalination. Does oxidation of MXene constitute a problem in MXene use in desalination applications?
For desalination, as I show, if we don't use the freeze dry, the MXene stacked, the desalination capacity is relatively low. But when we achieve porous MXene, the story change. So we can achieve much higher desalination capacities.
Mm-hmm. Thank you. And at the end, a couple of questions related to supercapacitors here. The question arrived about the charging response time of MXene supercapacitors conventional to compared to conventional. I'm probably mean the person probably means carbon supercapacitors.
So in this case, we just tested for desalination. We didn't test the time response. We just focus on the capacitance.
Mm-hmm. Thank you. Let me actually add from myself to this, because of much higher conductivity of MXenes compared to activated carbons or reduced graphene oxide, it is potentially possible to achieve a significantly faster response in general.
Yes, I agree. Yeah.
Yeah. And the last question before we're going to intermission is a little bit tricky one. So is a MXene material for batteries or supercapacitors in your opinion?
I think MXenes definitely can be used for supercapacitors, but also can be used for conversion chemistry-based batteries, not insertion type of batteries. The insertion type batteries, we still facing the problem related to the irreversible capacity in the first cycle. But for conversion batteries such as lithium sulfur battery, sodium sulfur battery, definitely MXenes have big advantages, because you can see the rich functional group, hydroxide, oxygen, and the fluorine contribute to the binding, naturally bind the lithium polysulfide and sodium sulfur polysulfide, so it can extend the cycle life. Yeah.
Well, again, thank you very much for covering such a broad range of energy conversion and storage topics in your presentation. I would like to thank you on behalf of the conference organizers and the audience. And now we are going to take a 5-minute break before moving to the next keynote talk.
So you're looking at a compound that we've created here at Drexel called MXene. We discovered it in 2011, but have recently learned how to make it behave like conductive clay. This stuff has the potential to replace the electrode material found in supercapacitors and even batteries. In the past, to create pure MXene films, you'd have to etch max phase with hydrofluoric acid, wash it, intercalate it with dimethyl sulfoxide, sonicate it, centrifuge it, and filter it. We've managed to cut the process down to just the etching step. Now, we simply react max phase with an etchant made from much safer acid and a salt, and after washing, we're left with a clay-like material that we can shape any way that we want, even rolling it out into a film. After drying, it's highly conductive. Not only is the process easier and safer, but electrodes that took us only 5 minutes to roll out have shown a 200% increase in capacitance over our previous reports. Sometimes the simplest ways are the best, and it's one of the many great things only happening at Drexel.
Well, welcome back to our second keynote talk, which will be delivered by Professor Chunmin Koo from the Center of Materials Architecture and Research at the Korea Institute of Science and Technology, KIST, South Korea. I'm sure many of you noticed his recent paper on extraordinary EMI shielding experience with titanium carbonitride MXene. Welcome to the talk. Before we start, let me also remind you about the webinar logistics to those of you who have not seen it yet. For those of you who have seen it half a dozen of times or more, you can ignore it. But the key thing is here, there is an opportunity to join by phone if your sound doesn't work. And also, please submit question to the chat box. We had a very large number of questions after the previous presentation, and it was really good to see such an excellent discussion after the talks here. And finally, If you miss the talk, it will be available later on the conference website. With this, please join me in welcoming Dr. Ku.
Thank you, Yuri. Yeah. Thank you all. Yeah. Good morning and good afternoon, good evening. Yeah, all. I'll share my screen first. Yeah, thank you, Yuri, again. And yeah, my name is Jongmin-gu from the Korea Institute of Science and Technology, the KIST. I also work for the pen. Yeah, I also work for the Korea University and the University of Science and Technology. Yeah, today's my talk title is 2D transition metal carbide and carbonitride MXenes for electromagnetic interference and shielding. Before I start my presentation, I would like to express my great appreciation to conference organizers, Professor Michelle Balsam and Professor Yuri Gogoji and Daniel Kapiko, for giving me a chance to present my MXene research result here in the memorable conference for MXene Research Society, MXene 2020, 10 years later. And I would like to express great congratulations to all of MXene inventors and researchers on wonderful achievement and advancement in MXene research just within 10 years after invention. MXene research community is growing very fast. I'm pretty sure the future of MXene is very bright, and MXene will be the center of nanotechnology research in the world. Personally, I also would like to thank Dr. Santoshi Yadav and Professor Giuseppe Palmigi. Actually, they invited me to Drexel University in early 2016. I met Yuri while giving an invitational speech at Drexel University. At the moment, I started the MXene research in collaboration with Yuri. It was a blessing to me and to my research. And I would also like to thank all my research collaborators, especially the Yuri, and also Professor Chulmin Bak and Professor Sang-Uk Kim and Professor Myung-gi Kim for their great support. And also, I would like to thank all my group members for their great contribution to this work. Actually, my group is researching on the synthesis of MXene and especially the synthesis of organic dispersions of MXene for improving the oxidation stability and the solution processability. And also we are researching on the several the application of MXene. Actually as many the speakers, including the Professor Vadim, the Michael Napkib, and the Miladin, Lobidik, in their talk, basically the MXene has seriously suffer from the degradation, especially in the water. For the first time, the Professor Yuri, they reported the MXene is very vulnerable to oxidation in water because of water and oxygen. The day before yesterday, also the Professor Vadim suggested the degradation of MXene is caused not only by oxidation but also by hydrolysis reaction in water. In the Yuri's publication, they also provided one solution for the degradation issue. Basically, degradation can be reduced or prevented by using the organic solvent instead of water. But problem is the MXene is just the well disposable in water, but not well disposable in the conventionally used organic solvent. The last year, my group reported in ACS Nano one very simple the method called simultaneous interfacial condensation reaction and phase transfer method. for preparing the surface functionalized MXene and their organic dispersions. By using this method, hydrophilic MXene flakes react with organic ligand at the interface between the water and organic solvent, and the surface functionalized flakes simultaneously transfer to the organic phase. Therefore, organic MXene dispersion can be fabricated in a single step without tedious purification steps. Recently, we developed a more efficient method, but it was not published yet, to surface functionalize MXene flakes. The MXene organic dispersion prepared through this method are very stable in various organic dispersion, even at very high concentration. As you know, the color of dispersion is the useful indicator for the good dispersion. For example, the TiC2, the MXene, well dispersed in an organic medium on a single sheet scale shows this kind of a clear, the greenish color. As you see, the surface functionalized MXene reveals clear greenish color in various organic solvents, indicating that the functionalized MXenes are well dispersible in various organic solvents, especially in non-toxic organic solvents such as methanol and IPA, isopropanol. And also, the surface functionalized, other type of MXenes are also very well dispersible in various organic dispersions. That organic dispersion reveals very strong oxidation stability, as the Uris group mentioned. And since the organic dispersion can exclude water and oxygen, therefore the organic dispersion can extend the storage time without degradation. Additionally, this organic dispersion with non-toxic organic solvents provide better the organic solution processability, even for hydrophobic coating on hydrophobic substrate. Due to high conductivity and good solution processability, the many plenary and keynote speakers in this conference, they already mentioned before, the MXene has many promising potential for many applications, including electrochemical energy storage, actuators, sensors, catalysts, and so on. My group also suggested several fascinating new applications of MXene, the microwave shielding, the terahertz shielding, and the Joule heater and LED application. The MXene can be used flexible and wearable and shape adaptable Joule heater due to their high electrical conductivity and very good solution processability. And also can be used as a transparent electrode for the polymer LED, the display application. And MXene also reveals very high microwave and terahertz shielding applications. Okay, from now on, let's move on to today's main topic, the EMI shielding of MXene. Here's the content, the table of content of my talk. In first, I will present a short introduction on EMI shielding and MXenes, and then the microwave shielding properties of carbide MXene and thin film MXene and structurally designed MXene films and carbonitride MXenes, and then the summary and perspective. Microwave shielding material is the material that helps to prevent electromagnetic interference, the EMI. The EMI is the disturbance behavior caused by strong electromagnetic induction and conduction mechanism between two electronic components in a close proximity. The EMI causes the serious problems, including the data loss, data misinterpretation, malfunctioning, and even failure of an electronic system. It may also affect the human health. That means we should solve this EMI shielding problem. The modern, smaller, and smarter flexible electronics require very highly stringent specifications such as lightweight, minimal thickness, flexibility, and transparency, and easy processability, along with excellent shielding effectiveness. The shielding efficiency is quantified by shielding effectiveness. The shielding effectiveness is defined as logarithmic, the ratio of the power of incident and transmitted wave, the total electromagnetic, the total shielding effectiveness can be achieved by the shielding by deflection and shielding by absorption and shielding by multiple reflection effect. Deflection, as you know, basically the deflection happens at the interface between two media having different reflective index over impedance, and absorption happens when the wave propagates in a shield. Intensity of the propagating the electromagnetic waves exponentially attenuate with the propagating path length that is the same as the sample thickness. Generally, the reflection and absorption, reflection and absorption are the function of materials property, including conductivity, permeability, and permittivity. For conducting shielding material, basically the reflection and absorption is strongly governed by conductivity. Larger conductivity produces the stronger reflection and stronger the absorption. And finally, larger shielding effectiveness. And the multiple reflection like this, multiple reflection can be caused by, multiple reflection also affect the shielding effectiveness, and the multiple reflection can be caused by the thin film, thin thickness, the effect, when thinner than the skin depth. And multiple reflection also can be caused by the internal, the interface of porous or the segregated structure, especially the multiple reflection by internal interface like this, significantly improve absorption and shielding efficiency due to their improved internal scattering effect. I will discuss this multiple reflection effect in detail later. Among shielding materials, basically the pure metal film is the most popular EMI shielding material because it has high electrical conductivity. However, the metal film is not very suitable for the highly integrated, smart, the flexible electronics because of their heavy weight and high cost and poor processability, especially the poor coating processability on the uneven shape of the substrate. 2D materials have been considered as a promising candidate for the lightweight shielding application. Among them, the MXene material is the most promising candidate for lightweight shielding. The many plenary and keynote speakers have already explained what MXene is. I think I don't need to explain it again. The MXene has many advantages, including the high electrical conductivity, up to 15,000 Siemens per centimeter, and low density, around 2.5 gram per mole, gram per cubic centimeter, and the good solution processability, such as spray, dip, and spin coating ability. These advantages are very good for the lightweight EMI shielding applications. In 2016, for the first time, Yuri and I reported the EMI shielding property of 3 different carbide MXene materials, including Ti3C2, Ti2MO2C, MO2C3, and Ti2MOC2. Among them, the Ti3C2 had the largest conductivity, around 5,000 Gm per centimeter, that had the best shielding performance, around 92 decibel shielding effectiveness at 45 micrometer thickness. And also MXene composite, composed of MXene and sodium alginate, the polymer, revealed very homogeneous the composite morphology and very high EMI shielding, shielding effectiveness that was quite comparable to the pristine MXene. Basically, the aim of shielding is to get high shielding effectiveness at low thickness, because shielding effectiveness can increase with the increasing thickness due to the attenuation of EM wave by absorption. As I mentioned in the theory, the Ti3C2 MXene and their polymeric composite outperforms all the shielding materials, even metal foils, at the same comparable thickness. 40 micrometer thick, the MXene film revealed 92 decibel the shielding effectiveness, that is equivalent to 99.9999994%. Yeah, the number of 9 is 9. So huge, yeah, so outstanding shielding performance is attributed to high electrical conductivity, as well as layered laminate structure of micrometer thick MXene films. Additionally, the abundance of the surface termination group can induce strong dielectric polarization loss that may also contribute to the outstanding shielding performance. Now, this paper is one of a highly cited paper. It was cited more than 1,200 times in 4 years. This paper stimulated nanomaterials and EMI shielding research community to join and work on the MXene materials research. Recently, the URI group also published very comprehensive the EMI shielding the property paper in ACS Nano. Actually, they reported 16 different the MXene materials EMI shielding property. They found the EMI shielding property is strongly governed by the electrical conductivity. So the Ti3C2 MXene had the best the EMI shielding property, and also that 16 different the EMI shielding material has the very broad spectrum in electrical conductivity. That means the people can choose the right one according to the shielding level of their own purpose. In previous papers, the micrometer thick the MXene films revealed very good EMI shielding performance. Nonetheless, the shielding mechanism was still not fully understood, mainly due to the challenge in preparing the monolayer thick MXene films. Recently, we fabricate a large area, the monolayer thick MXene film with uniform thickness by using interfacial self-assembly method. I will not explain the detail, the fabrication method, but briefly, the exfoliated, the MXene flakes float and assemble each other on the water surface to form large area assembled monolayer film due to Rayleigh-Bernard convection and Marangoni effect. And then the assembled monolayer film is transferred to the substrate, and film thickness is controlled by the multiple stacking of the assembled monolayer film. We studied the shielding property of systematically the thickness controlled assembled MXene thin films. Figure shows the total shielding effectiveness SET and shielding effectiveness by reflection SER and shielding effectiveness by absorption SEA of assembled films. SET, SER, and SEA increase with the increase in the thickness, and also the experimental data. The symbol is from experimental data and dotted line is from the theoretical calculation. The experimental data agree well with the theoretical calculation considering the multiple reflection effect by same thickness. An interesting point is that minimal commercial shielding requirement, the 20 decibel, the 99% shielding, is achieved just at 55 nanometer thickness. And for real lightweight shielding application, absolute shielding effectiveness, SSET, should be considered. It is defined as the shielding effectiveness divided by density and thickness. The larger SSET, absolute shielding effectiveness value, is desirable for lightweight EMI shielding application. The assembled thin film had ultra large SSET value over 3 million. That is the largest values among the shielding materials ever reported. It indicates the MXene is the best candidate material for lightweight EMI shielding, especially for ultra-thin coating applications. In 2015, the Professor Haobin Zhang and Zhongshen Yu from the BUCT in China published one interesting paper on MXene porous foam. They fabricated MXene foam by using hydrogen treatment. After hydrogen treatment, compact the MXene film expand the more than 600%, then form porous foam structure like this. The expanded foam structure enhance internal scattering effect and improve the shielding effectiveness from the 50 decibel to 70 decibel for 6 micrometer thick MXene film. This paper stimulates to investigate the structural design effect of MXene materials. Yuri and my groups also reported the EMI shielding properties of well-aligned and highly porous MXene and MXene CNT hybrid aerosols. This aerosol fabricated by bidirectional freezing method. That aerosol revealed well-aligned lamella-like porous structure supported by the column. The prepared aerosol was light enough to stand on the flower without collapse, and it also had very strong mechanical property and good shielding performance, even at very low density, 0.06 gram per cubic centimeter. Such shielding performance is attributed to the improved absorption property that is caused by improved internal scattering at the internal multiple interface. The internal scattering effect is also observed in the segregation structure. We prepared the MXene polystyrene segregated composite composed of the MXene flakes and polystyrene beads, SET, R, and SEA increase with the increase in the surface area of insulating polymeric domain in the composite. This is the first direct evidence that shielding performance is quantitatively proportional to the area of multiple interface in the segregated structure. This result also agree well with the theoretical calculations. We discussed in detail about the structural design effect in a review paper recently published in Advanced Functional Material and also in a book chapter of the first MXene book entitled 2D MXene for the entitled 2D metal nitride and metal carbide and nitride MXene, the book. The shielding performance depends not only on the intrinsic property, but also on structural design. Basically, MXene has very high shielding performance due to the intrinsically high electrical conductivity. Additionally, introduction of porous structure and segregated structure to the MXene can reduce the density and provide additional surface interface for enhancing internal multiple reflection effect. As a result, the structural design improve shielding effectiveness as well as the absolute shielding effectiveness, SSET. It indicates structural design is essential for lightweight shielding applications. Very recently, 2 weeks ago, we reported the abnormal shielding property of carbonitride Ti3CN MXene in Science journal. The Ti3CN, the carbonitride, has the same crystal structure as Ti3C2, but some of carbon were randomly substituted by nitrogen atoms. As synthesized Ti3CN nitride MXene, lower electrical conductivity than Ti3C2. So Ti3CN has lower the shielding performance than Ti3C2. But after the mild heat treatment, the shielding performance of Ti3CN significantly improved. So the heat-treated Ti3CN has much larger shielding performance than Ti3C2. Heat treatment increased the conductivity a little bit, as well as porosity of both Ti3CN and Ti3C2. Ti3CN revealed a little larger porosity than Ti3C2, but annealed Ti3CN had still lower conductivity than Ti3C2. The maximum porosity of Ti3CN is around 15%. Interesting point is that improved total shielding effectiveness is mostly caused by improved absorption property, since the shielding by reflection is rarely affected by the heat treatment. In an optimal condition, Ti3CN revealed 116 shielding effectiveness at 40 micrometer thickness. The heat-treated Ti3CN carbonitride outperformed all the shielding material, even the Ti3C2 MXene. That anomalously improved the shielding, absorption shielding, SEA, and total shielding effectiveness, so partially attributed to the improved porosity and conductivity. However, these factors alone do not fully explain the observed increase within the frame of existing shielding theories. It is much larger improvement than our expectation based on the theoretical calculations. At this stage, we suggested that anomalously improved absorption may be caused by the metastructure effect that can improve the effective permeability and permittivity, and finally, the improved absorption property. These results provide guidance for designing the lightweight EMI shielding materials, but also highlight the need for exploring the fundamental mechanism behind the interaction between the electromagnetic wave and the 2D materials. In summary, the 2D MXene has much larger EMI shielding effectiveness than any other synthetic materials, and also the MXenes exceed the 20 decibel just at 55 nanometer, indicating the high feasibility to ultra-thin coating, and annealed TiC and revealed the anomalous absorption property due to the structural effect. In perspective, the theoretical mechanism study on the MXene material should urgently be explored, and also in-depth study on the meta-structure effect should be investigated, and new structural design work is also open for future shielding research, and tunable surface termination of MXenes, flakes, and new types of organic dispersion work with the new organic ligands are requested for further improvement in solution processability, and magnetic MXene need to be explored for paradigm shift of shielding the research. Until now, no magnetic MXenes are available, but if the magnetic one is available, I'm pretty sure the magnetic MXene will make the strong paradigm shift in MXene shielding research. This conference is for celebrating 10 years anniversary of birth of MXene. It passed only 10 years after invention. The MXene research is still at early stage. As Professor Johanna Rosen and Babak Anasori mentioned, still there are many opportunities to find and synthesize new MX and MXenes. That means the opportunity for the MXene shielding research are also open. Therefore, I'd like to encourage you, many researchers, to participate in this interesting topic. And this work was supported by this project. And I would like to also, thanks again for the collaborator and the group members for their support. Thank you for your attention.
Well, Chunmin, thank you very much. This was outstanding. Clearly, MXene is the best material for EMI shielding now. And we are running a little bit late, so I won't be able to ask most of the questions. We received a very large number of questions. But let me start with the question of my conference co-chair, Professor Barzoum. Why do you qualify MXene as better than any synthetic material? Are there any natural materials that show a high electromagnetic interference shielding?
I mentioned in my talk, basically the outstanding the EMI shielding property of MXene is basically from the intrinsic property of the MXene, such as very high electrical conductivity. Also, the intrinsic, the structural, the feature of MXene has the 2D nano structure. So if we make the film, that the forms kind of well stacked the laminate structure. That laminated structure also the function as the multi shield. So it is a very strong, very important feature of the MXene. And also, this the MXene is a very useful material to control the structural design, structurally designed the material. So for example, I mentioned in my talk, we can easily make the highly porous and very nice the segregate the composite structure. That kind of a structural effect also can improve their properties. So both this intrinsic property of MXene and also the some kind of a processing the feature can make this MXene is very special for this application.
Right, but there are basically no natural materials that would be able to compete either. Am I right about it?
You mean if we compare the MXene with the natural material?
Yes.
Basically, we also compare with the many the natural material, especially we also to compare the property of MXene with the property of the metallic material, the foil, the things, and basically at the our result showed that the MXene material has very comparable the EMI shielding property as the pure metal, not the metal particle. Actually, basically is quite much better than the metal particle, but it's very comparable to the pure metal film. Yeah, so this is kind of very outstanding and very special property.
Chunmin, sorry to cut you off. But let me ask also a question related to the earlier part of your talk about dispersion of MXene organic solvent. The question arrived asking that you used ligands to drag MXene flakes from aqueous phase to the organic solvent. How do you remove the ligand when it comes to applications to restore the intrinsic properties of MXene?
Basically, very good question. Basically, I mentioned two different methods. One is the interfacial self-assembly. Actually, I expressed that interfacial, the reaction method is the one-step process. But as you mentioned, if we need to separate the residual, the organic ligand, we need to use the purification step, once the purification. But basically, organic ligand is very essential for the surface functionalization, but also that is not for the electrical conductivity. So we need to minimize the organic ligand for that surface functionalization.
Okay, we already got deep into the break time between the talks, but let me still ask you the last question here. What is the role of polymers, role of oxidation, and role of porosity in the electromagnetic interference shielding efficiency? Actually, I'm combining three different questions into the last question, and there are probably 24 questions which we won't have time to discuss now.
Basically, for the EMI shielding application, the polymeric binder is sometimes very important, to improve the mechanical property and to improve the durability of this material application. Basically, but the one advantage and one disadvantage. Basically, one advantage is we can improve the kind of mechanical property also, and we can prevent the oxidation from the oxygen in air, because the polymer can protect, polymer can passivate the surface of the MXene. That means the MXenes can improve the oxidation, the stability. But one disadvantage is the conductivity. Basically, if we add the plenty of the polymeric binder, actually we lose the electric conductivity of the MXene. So actually, again, the polymer is also the insulating organic material. So the ideal the system is we need to minimize the organic polymer and organic the ligand, but we need to add that material to improve the mechanical property.
Thank you very much, Min, once again. Unfortunately, we have to miss the intermission and move to the next talk, but there are lots of other questions. I'm sure the organizers will forward them to you that you may wish to respond to people who ask a question directly. And again, of course, feel free to contact Professor Chong-Min Koo regarding questions related to electromagnetic interference shielding properties of MXenes. Thank you very much. And with this, we are going to move to the next talk. Our next speaker is also a good colleague and friend who actually spent half a year at Drexel University in the past as a visiting professor. And this is Professor Bin Shu. Many of you also know him as the organizer of the second international conference on MXenes in Beijing last year. Professor Shu is with the Beijing University of Chemical Technology here. Bin, welcome.
Okay, can you see my screen? Okay. Hello, everyone. It's my great honor to give a talk in this conference. Today, I will talk about MXene-based materials and electrodes for energy storage. As we know, MXene is a new family of 2D materials. Up to date, more than 18 types of MXenes have been theoretically predicted, and about 13 different MXenes have been synthesized. MXenes combine the properties of both graphene oxide and reduced graphene oxide, including metallic conductivity, good hydrophilicity, mechanical properties, and structural varieties. So these unique properties makes MXene have wide application in various fields, including energy, catalysis, electronics, biomedicals, environment, and sensors. Among these applications, the energy storage is one of the most important one. MXenes are promising for energy storage due to the following reasons. The layered structure of MXene can accommodate various cations, such as lithium, sodium, potassium ions. MXene usually have metallic conductivity up to 15,000 Siemens per centimeter. MXene have rich surface chemistry and pseudo-competitive properties. So MXenes have very good rate performance. Freestanding and flexible electrode can be easily prepared by vacuum assisted filtration. So MXene can be used in flexible variable devices. These properties make MXene have wide application in various energy storage devices, such as lithium, sodium, potassium ion batteries, and also lithium sulfur batteries, supercapacitors. From this figure, we can see that the publication of MXene are growing fast in recent years. Among these publications, energy storage field account for a large proportions. This is my outline. I will talk about our recent work on MXene for energy storage in following three aspects. The first part about MXene as active materials. In this part, most of our work focuses on structural control of MXenes. MXenes can be used as active materials for supercapacitor and batteries. However, the layered restacking of 2D nanosheets results in dense and stacked structure of MXenes. This will lead to long air transport pathways and inferior accessibility of MXene surface X to the electrolyte, and thus limiting the energy storage capacity and rate performance. To solve these problems, the structural control is very necessary. There are two ways. One is expand the interlayer spacing. Another is construct a 3D porous architecture. So firstly, to enlarge the interlayer distance, we proposed a very simple but effective method to prepare MXene film by natural sedimentation instead of the conventional used vacuum filtration. The film prepared by natural sedimentation is freestanding with very good flexibility. As EM and XRD indicate that the MXene film prepared by natural sedimentation has an increased thickness and expanded interlayer distance. The thickness and interlayer distance was influenced by the solution concentration of the MXene solution. The lower the concentration, the more those structures will be obtained. The enlarged interlayer spacing facilitates lithium air accessibility. Therefore, the MXene film exhibits enhanced lithium storage capacities. It can reach 350 mAh per gram, almost double larger than the conventional prepared MXene films. It also shows excellent cycle stability and superior read capability. Transform 2D MXene nanosheets to 3-porous architecture is also an effective way to solve the restacking of MXene films. As we know, template method is a very effective method to create porous structure. Sulfur is easily to control the particle size and can be easily removed by sublimation at a temperature higher than 300. So we use the sulfur as template to create a porous structure by mixing the sulfur and the MXene in solution and following the filtration and thermal treatment at 300 for 3 hours to remove the sulfur. We can see that a porous developed porous structure are created. The higher the sulfur template, the more developed porous structure can be obtained. The 3D porous structure offers massive active sets and sufficient air transportation channels, and a smaller electrolyte contact angle facilitates the electrolyte filtration. The 3D porous MXene forms exhibit much enhanced capacitance. The capacity can reach nearly 500 mAh per gram for lithium storage. It also shows very stable cycle performance and also very good rate performance. It can output 100 mAh per gram at 18 ampere per gram. This is a very large current density. A terminal-like MXene was fabricated facially by coating a carbon layer on 2D MXene nanosheets through the self-polymerization of dopamine on MXene nanosheets, followed by freeze drying and carbonization. The self-polymerization of dopamine on the surface of MXene not only facilitates the transform of 2D MXene to a tremolo-like structure, but also formed a thin carbon layer on the MXene surface. The carbon layer with a mass ratio of 9% preserve the MXene from air oxidation and self-aggregation. The 3D porous carbon-coated MXene exhibit expanded dispensing and developed porous architecture. This unique structure makes the carbon-coated MXene shows very good electrochemical performance in both lithium air batteries and sodium air batteries. For lithium air storage, a capacity of nearly 500 mAh per gram was obtained, with high pseudo-capacitive contribution. For sodium air storage, a very stable capacitance was obtained during 3,000 cycles. A very small capacity decay were observed. We also prepared the porous MXene films by ice template. The porous MXene films were prepared by freeze drying the MXene-based hydrogen films. The interior residue water during the freeze drying were converted to small ice grain, which act as template to create a porous structure. The introduction of carbon nanotubes in the interlayer increased the interlayer water and make a more developed pore structure. Compared with the dense structure of the vacuum-dried MXene film, the ice-temperature MXene film shows a porous structure. We can see many large pores. The film is freestanding and can be directly used as electrode materials for supercapacitors. Due to the opened structure and the increased active surface sets and the good transportation of the airs, these materials shows a very high capacitance and very good cycle stability in supercapacitors. In addition, we also provide an efficient and time-saving method for constructing 3D structure by employing the self-propagating reduction of graphite oxide. Firstly, we prepared the MXene graphite oxide film by vacuum filtration the suspension of MXene and graphite oxide. When the MXene graphene film was slightly touched the 300 heating plate, the self-propagating reduction of graphite oxide was initiated, and this process can be accomplished in a very short time, only 1.25 seconds. During the reduction of graphite oxide, a large amount of gas were released. So the dense structure of the MXene film was opened and creating a very developed porous structure. This structure can provide massive air accessible active sets and promotes fast air transport. So being used as electron materials for supercapacitors, it exhibits very good performance, including high capacitance and very good cycle and rate performance. The second part about MXene-based composites. In batteries, some active materials such as silica, metal oxides, and phosphorus are promising anodes for batteries due to their high capacitance and low cost. However, these materials suffer from low conductivity and large volume change during charge discharge. MXene can help to solve these problems by acting as a substrate. Because MXene has metallic conductivity, so it can improve the conductivity of the composites. The 2D structure can alleviate the volume change and prevents aggregation of the active materials. The rich surface chemistry makes the accessibility very easy. So MXene-based composites is an effective method to develop advanced anode materials for batteries. I will introduce 3 strategies. The first one is van der Waals self-assembly. MXene, when we mix the MXene and metal oxide nanostructures in THF, the metal oxide nanostructures will assemble on the surface of MXenes. With this method, we prepared 2 composites. We assembled TiO2 nanorods and tin oxide nanowires on MXenes surface. We can see both of them are evenly distributed on the surface of MXene nanosheets. In this composites, MXene provides the good conductivity and also alleviate the volume change of the metal oxides, and also prevents the aggregation of nanostructures. And these nanomaterials can also prevent the restacking of MXene nanosheets. The synergy of these 2 composites make the heterostructures shows a very good lithium storage performance, especially cycle and rate performance. TM observation indicates that no noticeable dissociation, collapse, or aggregation were observed after long cycle measurements. This confirms that MXene-based composites has very good structural stability. As we know, MXenes are negatively charged, so MXene-based composites can also be easily prepared by electrostatic self-assembly, the positively charged metal oxides with negatively charged MXenes. With this method, we prepared two materials. Both of them show very good cycle and rate performance. In this work, we prepared MXene carbon nanotubes phosphorus nanohybrids through a ball milling method. The carbon nanotubes were introduced to MXene nanosheets to construct a conductive network, and then MXene and the carbon nanotubes were combined with red phosphorus by ball milling. During this process, the oxygen-containing terminations of MXene interact with phosphorus, forming TiOP bond. This bond favors the good electronic contact between red phosphorus and MXenes. It also benefits the structural integrity during charge discharge. Due to the high capacity of phosphorus, the good conductivity, and also the stable TiOP bond, the nanohybrids exhibits a very high capacitance, about 2,600 mAh per gram. It also shows a very stable cycle performance and also very good cycle performance, rate performance. It can output 450 mAh per gram at 30 C. So the third part, I will discuss about MXene as a multifunctional conductor binder. As we know, from the view of device performance improvements, the electrofabrication is as important as active materials. However, many efforts have been done to adjust the structure of the active materials, but few works focused on the electrode fabrication. So from active materials to electrodes, there are large opportunities for us to develop the energy storage device technologies. Here, we proposed a new strategy using 2D materials like graphene and MXene as a multifunctional conductor binder to construct electrodes for batteries and supercapacitors. For example, porous carbon are usually prepared the electrodes by coating the slurry of porous carbon and conductive additive, and also the polymer binder such as PVDF, PTFE, CMC, etc. The usage of polymer binder has some shortcomings. These materials are electrical insulator, so it is adverse to the energy power density of the devices. And also polymer binders are electrochemical inertness. Usually it will occupy 5 to 20% weight, but cannot provide any capacitance. The electrode fabricated by polymer binder has insufficient mechanical properties, so it cannot meet the requirements of flexible devices. Sometimes we worry about the polymer binder will block the pores of porous carbons. Although polymer binder has so many shortcomings, replacing it is easy thing. It is a challenge. Using 2D conducting materials like graphene and MXene can solve this problem. Graphene and MXene have very high conductivity and electrochemical activity, excellent flexibility, highly exposed surface. So they can act as conductive activities and also flexible backbone. So it is expected to obtain the better performance and good flexibility. So 2D graphene and MXene are promising candidates for replacing the conventional polymer binders to fabricate flexible freestanding electrodes with superior performance Firstly, we use the reduced graphite oxide as a multifunctioning conductor binder. The process is very simple. Only by mixing the porous carbon with graphite oxide in water and ultrasonication to get an evenly dispersed solution and vacuum filtration, then thermal reduction at 300 for 3 hours to make the gel reduced to R-gel. We can see that the obtained film is freestanding with very good flexibility. ICM indicates that the R-gel bonded electrode shows a loose structure with large pores. The graphite oxide constructs a 3D network and the activated carbon particles embedded in. So this structure facilitates the air and electron transformation. Being measured in aqueous electrolyte, the R-gel bonded electrode shows higher capacitance, better rate performance, and lower resistance compared to the conventional PTFE bonded electrolyte. The thickness is controllable from 28 to 250 micrometer, so it can meet the requirements of different supercapacitor design. And the carbon quantity is also controllable from 15 to 19%. Most importantly, this method is universal. With this method, we fabricated powdery carbon, fibrous carbon, and spherical carbon to freestanding flexible film with better performance than conventionally PTFE bonded electrode. Being measured in non-aqueous electrolyte, the advantage of R-gel bonded electrode are highlighted. We can see that the R-gel bonded electrode shows larger surface area, larger pore volume, and higher conductivity, and the capacitance 40% larger than the conventional PVDF bonded electrode. And especially the rate performance is outstanding. It can endure a very large current density of 600 ampere per gram. Similarly, we consider MXene as a conducting binder to fabricate porous carbon for supercapacitance. Only by vacuum filtration, the mixed solution of MXene and activated carbon. Only for this simple process, we can get a freestanding flexible film. As MXene itself is conductive, so no reduction process is needed. That is to say, this process is not only simpler than the conventional coating method by polymer binder, but also simpler than R-gel binder. From ICM, we can see that the activated carbon particles encapsulated in MXene nanosheets. We can also observe some large pores. We measured the electrochemical performance of this film in a symmetrical two-electrode system with organic electrolyte. You can see, compared with PVDF bonded electrode, the MXene bonded electrode shows higher capacitance and better rate performance, and much lower resistance. This is because of the metallic conductivity of MXenes. The electrode also shows a very good rate performance. It can endure a very large scan rate of 4 watts per second. This is a very large scan rate. The MXene binder can also be used in electrode fabrication of batteries. As we mentioned previously, silica is a very promising anode material for lithium-ion storage due to its very high theoretical capacitance. However, it suffers from large volume change during child discharge and poor cycle life. With MXene as a binder, a freestanding carbon-coated silica film is easily prepared. And this film is freestanding and has very good flexibility. As a multifunction binder, in this case, MXene can not only provide the good conductivity and better air transpiration, and most importantly, it can construct a loose and porous structure to buffer the large volume expansion of silica during charge discharge cycle. This is a very important properties for silica electrolytes. It can improve the cycle performance. With the improved conductivity and buffer effect, this MXene bonded carbon-coated silica film shows higher capacity, better read performance, and very lower resistance. ICM indicates no obvious cracks were observed after long cycling measurements, much better than the conventional CMC and PVDF bonded electrode. MXene bonder can also be used for carbon electrodes for sodium and potassium air batteries. We know that hard carbon is a good materials for sodium and potassium air batteries. However, as sodium and potassium has a larger air size than lithium airs, so the cycle performance of hard carbon is not very satisfactory due to the large volume change during charge discharge. Using MXene as a bonder, we can solve this problem. The fabrication process is very simple. We can only vacuum filtration the mixture of MXene and hard carbons. And from ICM, we can see the hard carbons are uniformly embedded in the 3D networks constructed by MXene nanosheets, and some large pores are formed between the MXene nanosheets and the hard carbon particles. We can see that the film has very good flexibility. It can be folded in the word MXene. Being used as anodes for sodium and potassium air batteries, MXene bonded hard carbon electrodes shows much better performance than the conventional PVDF bonded electrode. We can see for sodium air storage, this is a PVDF bonded electrode. This is for MXene bonded electrode. It has higher capacities and very stable cycle performance. During 1,500 cycles, no capacity decay were observed. For potassium air batteries, we can see the capacities of MXene bonded electrodes decay very quickly. But for MXene bonded electrode, the cycle performance is very stable. So MXene can effectively stabilize the film structure and buffer the volume expansion of hard carbon. These methods can also be extended to lithium sulfur batteries. Previously, we prepared the small sulfur carbon electrode, which can avoid the shuttle effect. To meet the requirements of flexible devices, we combined the MXene bonder with the small sulfur electrode. By simple vacuum filtration, the mixture of these materials is MXenes, and we can also get a freestanding flexible film. Compared with the conventional PVDF bonded electrode, this MXene bonded small sulfur film also shows better cycle performance and read capabilities. This is my conclusions and perspective. Due to limited time, I will skip this slide. In last May, Professor Yuri Gogutz and I organized the second international conference on MXenes. The conference attracted 450 attendees. To celebrate this conference, hosted by Beijing University of Chemical Technology, Yuri and I organized two special issues. One is in advanced functional materials. Another is in Chinese chemical letters. The special issue in advanced functional materials include 7 reviews, 1 progress report, and 14 original research papers. The topic covers the synthesis and structure of MXenes and the application of MXenes in energy, environment, optics, electronics, catalysis, and biomedicines. Here are some of the papers. all the articles are online for reading. For the special issue in Chinese Chemical Letters, it has been published in April. Here is the download link. Welcome to read these papers. At last, I'd like to thank the hard working of my students, especially彭章、宁孙、倩照、蓝颖瑜、欢流、嘉伟妙, and others. And also thank my collaborators, Professor Yuri Gogutsi, Paris Simon, and Dr. Babake. And also thank the financial support of the fundings. Thank you for your attention.
Bin, thank you very much for this talk covering a lot of ground, many applications of MXenes in energy storage. And I'm particularly impressed by use of MXene as passive material. There are many activities in the world about use of MXenes in active materials in battery supercapacitor, but really the role of binders, current collectors, and other is often overlooked. A few questions. What are the drawbacks of MXene as a material for supercapacitor? Nothing is perfect probably in the world, not even MXene. So drawbacks, what are the problems with MXene use in supercapacitors?
Okay, I think MXene is a very promising electronic materials for supercapacitors. I think the advantages including the metallic conductivity. It is much higher than the conventional porous carbon. So this is a very important advantages. And also the large density is also a good, very important advantage. So the volumetric capacitance of MXene is much larger than any active materials of conventional supercapacitor. I think this is very important. But for the problem, I think the layered structure of recycling of MXene nanosheets, this is a problem. The layer recycling will block the air's transformation, so it is a long distance to transfer. So creation porous structure is very important. I think it will improve the rate performance. But for practical applications, we want to combine the high volumetric capacitance and good rate performance. So I think we need a balance between these two factors. I think this is very important. So we should adjust the porous, not too much, not too large, and a balanced porous structure is okay, I think.
Thank you. What current collector did you use for MXene supercapacitors?
We know that MXene is freestanding and it can be directly used as electrode for supercapacitor.
Very important, very good. I think this is a very important message to the community. You win just by eliminating current collector already. Here. Let me move to the next question. Sorry to keep you short because we're running out of time. Did you study the temperature effect on capacitance of MXene supercapacitors?
Oh, sorry. I have not tried to investigate the effect of temperature on the supercapacitor performance, but I think MXene will have good low temperature performance and high low temperature performance, I think, because it has a very good conductivity. But for high temperature, I think maybe we should pay attention to the oxidation of MXene, because we know MXene is easy to be oxidized. So I think this is a very interesting work. We should try the temperature effect of the MXene to meet the requirements of different environments.
And for the sake of time, let me ask the very last question. is there any interaction between carbon atoms in graphene, reduced graphene oxide, and MXene surface in hybrid films?
Okay, I think when we prepare the composite film of graphene oxide and MXene, I think maybe there will be some interactions because MXene graphene oxide has rich surface oxygen containing surface functional groups, and MXene also has some OH and fluoride groups. So I think maybe it will have. And what's the most important is that when we combine the graphene oxide and the MXene, we must pay attention to the oxidation of MXene by graphene oxide. So usually when we combine these materials, we will take care of the oxidation of MXene.
Okay. Bin, thank you very much for your presentation. Again, there are many other questions. We just don't have time, but thank you to everyone for submitting those questions. It's exciting to have such an interest to the talks and also have a good discussion after every presentation. With this, I would like to thank all the speakers in our first session.
Okay. Thank you, Yuri, for moderating this really fabulous panel. I learned a lot just sitting here in the last half hour that I did not know, especially about graphene. I want to go back to one thing that I learned. If you're going to compete with another material, going back to Terence's last point, what I learned is that you have to make it better and cheaper than what's available. Well, that's as simple as that. You got to make it, if you can make something that's cheaper and performs as well as what's available, then people will, come to you. All right. So with that, alas, here we are at the end of this conference. I hope the audience, you agree with me that all the talks were truly exceptional and certainly world-class, plus the two panels, present company accepted. I also like to take this opportunity to thank all of the speakers for taking their time and sharing their perspective. It was really very gratifying. Now, as superb as the talks were, this entire operation would not have been possible without people behind the scenes. So for the poster sessions, I would like to especially thank Asya Saricheva and Mark Anai. And really the people who deserve an amazing amount of thanks and gratitude for doing an absolutely outstanding job was Miss Christine Chang, person who's behind the scenes moving all the screens around, Miss Gwen Grasberger, who has been just unbelievable since the beginning of this idea. And I really thank you, Gwen. And then last but not least, Ms. Danielle Copico. It's been a pleasure working with Danielle. She is incredible. Like I said, we would not be here without her. So from all of us here at Drexel, we thank you for taking part in this virtual conference. This was this was not anticipated, let's just put it this way, but we pulled it off. And then, to help us better meet your needs, if you can complete the survey you'll receive by email after this webinar, tell us what you think worked, tell us what you think didn't work, would be very helpful in case we have to do another virtual conference. And then lastly, and most importantly, we really look forward to welcome you all to Philadelphia for our next MXene conference a year from now, MXene 2021. Thank you very much.
The word Philadelphia means brotherly love. and it seeps from every inch of our city. It's a way of life, a type of thinking that draws us closer to this city and each other. It's who we are. It's how we breathe. It's why we care so much about what we create, about the devotion we flaunt, the flavors of our culture, and the history that makes us. Brotherly love is what we feel in each other when the music makes us sway and move, and the city's buzz draws us together. It's what drives our compassion for a person we have never met. Because even though we can feel isolated by our many differences, the spirit of this city flows throughout its diverse communities and connects us all. This city is more than a revolutionary town. It's a hub of artists and innovators, of scholars and visionaries. And anyone who chooses Philadelphia joins a community of strong, proud individuals, united by our passion for life and each other. This is an invitation to be yourself and experience a family without bounds. Brought together in unexpected ways.